lots of different ways of looking at this formula. I'm going to start with the most convoluted way, and then I'm going to go to the more easy one. So I've got a sequence here: 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. And I remember one of the things I noticed a long time ago when I was trying to figure it out was 1 plus 8 is equal to 9, 2 plus 7 is equal to 9, 3 plus 6 is equal to 9, 4 plus 5 is equal to 9. And that's not something just limited to this particular sequence. If I do 1 plus 2 to 7, 1 plus 6 is equal to 7, 2 plus 5 is equal to 7, 3 plus 4 is equal to 7. And it's going to be like that for all numbers. So from here, am I able to come up with a formula to predict what the sum of everything is going to be? So the first thing I noticed was that, like I said, all of these add to 9. So they have an average value, since it takes, all of these are equal to 9, but it takes 2 of them to equal 9. So they're going to have an average value of 4.5. And how many pieces are there? If each one is about 4.5, and there are n minus 1, it's whatever the last number was in the sequence minus 1, because I start with the number before the last number. In this case, it's 8, n minus 1. So this part of the formula counts this part that I've drawn on. 1 plus 8 is equal to 9, 2 plus 7 is equal to 9, 3 plus 6 is equal to 9, 4 plus 5 is equal to 9. And the last thing I didn't include was just the last number itself, 9, so plus n. And if I look at this formula, it follows the same pattern. I've got all of these things that add to equal 7, but it takes 2 of them to do that. So they're going to have an average value of half of 7, because they're like halves of 7. They're little like Legos that go onto each other. I don't know, like puzzle pieces, that all equal the same shape. And the same thing, how many of these halves are there? There are n minus 1 of them, in this case 6. And finally, that just accounts for this part. I've got to account for the last part, the 7, so plus n. If it was 11, then I would have 10 halves of 11 plus 11 itself, and then I would have my total. So one thing that should be noticed is that I picked odd ones, and now I'm going to do an even one. It's not different in any way, but it's easier to understand this one first and then to look at an odd one. Just to understand the idea of, look at these different halves that add to equal the final number. That was the main point of this. But I'm going to do an even one. I know you were worried for a second. I'm going to do it. 8 plus 9 plus 10. So if I do the same thing, it doesn't change at all. 9 plus 1 is equal to 10, 2 plus 8 is equal to 10, 3 plus 7 is equal to 10, 4 plus 6 is equal to 10, but I've got this 5 here. See, if I had started with this one, people would have been flipping out. I would have flipped out. Actually, I think that's what caused me to flip out in the first place, like in 9th grade or whenever, when I was looking at this. I didn't really flip out, but it's just easier to see the other one, to start with the other one. Because if you notice, it's going to be exactly the same thing. I've got all of these halves that add to equal 10, but the only thing is I have an extra half left over. But still, the same formula applies. All of these numbers before the final term of the sequence are going to have an average value of half of that final term. And how many of them are there? There are going to be n minus 1 of them. There are 9 when I go to 10. And still, that only accounts for this part in green and my little half. Still doesn't account for the 10, so I've still got to add plus n. Didn't mean to do that. And I'll do one really quickly for 8 as well, but it should be pretty obvious by this point that of course it's going to work. It's infallible. 1 plus 7 is equal to 8, 2 plus 6 is equal to 8, 3 plus 5 is equal to 8, and I've still got that half. Still, they have an average value of 1/2 of the final term of the sequence. And there are n minus 1 of them. There are 7, n minus 1. And I've still got to add my final term. But I might say that this doesn't look anything like this. But I beg to differ. Multiply it out. Now I'm going to multiply this top and bottom by 2 so I can put it over the same fraction. So actually, you know what? I'm just going to erase that and just go ahead and do that. So look at that. That's right. You thought it was wrong, but it really wasn't. So yeah, I got the same formula by thinking of it in this way. And technically these other methods, so to speak, they're not really other methods. It's really the same thing, but thinking about it in a different way, which can be important sometimes in math because most people don't think the same way. And a lot of times in a math class they'll say this is the way to think about it and do it, and I know plenty of times I was just like, well, I think of it a different way, so sue me. But that's one way. And this will be a different way of thinking about it. It's the same thing, but it's just different. And these ones are easier. So another way of thinking about it, I've got a sequence, is to look at the sequence and say, well, 1 plus 10 is equal to 11, 2 plus 9 is equal to 11, 3 plus 8 is equal to 11, 4 plus 7 is equal to 11, 5 plus 6 is equal to 11. Change of color. Okay, so I've got all of these halves that equal 11. So all of these are valued at 1/2 of 11, basically. N plus 1 over 2. And how many of them are there? Well, there are n of them. There are 10 in this case, n. So that one was really easy. Why did I even bother showing the other one? Some people think differently. What can I say? I thought the other way first. That's probably why I didn't get into all the really good schools. Anyway, let's do an odd one. One plus 9 is equal to 10, 2 plus 8 is equal to 10, 3 plus 7 is equal to 10, 4 plus 6 is equal to 10, and I've got this stray 5. But again, they are still, on average, equal to half of 11. Or 10. Now you really know why I didn't get into all the good schools. To half of 10. Add these together. 10, 10, 10, 10, 10. They're on average equal to, because it takes 2 of these little bits to equal 10. That means on average, these little bits are worth half of 10. And there are 1, 2, 3, 4, 5, 9 of them. There are n. So that was a much easier way of getting this. And there's still one more way of thinking about it. And I think this was supposedly the original way that it was discovered. I don't know if this is true or not, but I remember a long time ago in an algebra class, I think it was like in high school, my teacher told me this story about how, like a long time ago, there was some kid in a math class. The teacher assigned them some problem, some addition problem. They were working on like addition and subtraction. So the teacher assigned, well, I want all you little children to add 1 plus 2 plus 3 plus 4 plus 5 all the way until 99. I guess just to practice their addition skills, and I guess he was expecting just to chill out and drink coffee or whatever it was back then and kick his feet up on the desk. But some kid apparently solved it really, really fast, and apparently this was the person who discovered it. I don't know if it's true or not. It was just some story. Maybe it wasn't the person who discovered it, but I don't know. It's just the story. It's just the story they tell in all those math circles. So he solved it really fast. Now, I'm sure everyone in the class is going, I'm sure if you even approach most people, especially if you didn't know that formula, they would go, okay, 1 plus 2 is equal to 3, 3 plus 3 is equal to 6, 6 plus 4 is equal to 10, 10 plus 5 is equal to 15. That would take a really, really, really long time. But what this kid did was, he thought, well, I've got this sequence is equal to something. 1 plus 2 plus 3 plus 4 plus 5, blah, 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 until 99. If I take that same sequence and put it backwards, ugly ass 7. Now it becomes a really easy problem, doesn't it? On average, they're going to be worth 50. And how many of them are there? There are 99 of them. Divided by 2, because this will add up to be twice of what that would be worth. So we thought of it like this. 2 times the sequence is equal to 99 plus 1 plus 98 plus 2, all the way down till you get back to 1 plus 99. So I wrote it out mathematically like this. S is equal to 1 plus 2 plus 3, we'll just leave it at that, plus n minus 1 plus n. And the other sequence, I didn't need to do that, n plus n minus 1 plus n minus 2 plus n minus 3 all the way to 1. So if you add these two sequences together, you get 2s is equal to n plus 1 plus n minus 1 plus 2 plus n minus 2 plus 3 plus n, no need to do any more. The last one will be n plus 1 again. So it's pretty easy to see that all of these are going to equal n plus 1, n plus 1. But how many of them are there? How many of these are there going to be? There are going to be n of them, whatever the sequence ends at. So this can be simplified as n times n plus 1. Since all of these are going to be equal to n plus 1, all that matters is what number n is. And then divide by 2. And there it is again. So I showed 3 different ways of thinking about it. Just pick whichever is easiest to remember. Probably this one's easy to remember, so you just put it backwards, but sometimes you just gotta do whatever the hell it is you remember.